Hi, my name is Brian Caffo, and this is the regression module in our Coursera data science track. And in this lecture, I'm going to go over some basic notation and background. And I'm going to try and minimize the amount of mathematics required for this class, but I won't skimp on the details. If you're interested in some of the math, that won't be the point of the class, but if you're interested in some of the math, I will cover it. But I should emphasize that neither calculus nor linear algebra will be required. The most you will need to be able to do is some basic algebra and summation notation, and that's about it. So let me get my pen here. Let's just start with some basic notation that we always use. We often describe a bunch of data points as, say, x1 to xn, where x1, x2 refers to the ordered list of data points. So, for example, if our data set was 1, 2, 5, then x1 would be 1, x2 would be 2, x3 would be 5, and in this case, n would be 3. And of course, we often use a different letter other than x. We often use y, and so we usually use letters to represent random things like random variables, and we'll use sort of an uppercase X to represent a kind of conceptual value of the random variable, and we use like a lowercase x to represent a number that we would plug into, so it would be meaningful to write, for example, that way. We often use Greek letters for things we don't know. So mu is a mean that we want to estimate, and we'll estimate it with a data level quantity x bar. Okay. So the empirical mean we can just define as simply this guy right here, and that's just the average, the 1 over n summation I equal 1 to n. So this notation right here just means add up all of the elements, and of course then we divide it by n. Notice an interesting thing that we'll kind of use quite a bit is if we take our data and we subtract off the mean, then the resulting data points have mean 0. And this is, let's just work it out really quickly. The summation of these xi tilde is equal to the summation of xi minus x bar, right? Which is equal to summation xi minus summation x bar. But this guy doesn't depend on I, so this is just nx bar because we've added x bar n times. And this guy is just the average, but we haven't divided by n, so this is also nx bar, so that's equal to 0. Okay, so anyway, this is the process is called centering the random variables. The sample mean is, of course, a measure of central tendency of the data. It's an attempt to define the middle, and in the previous lecture, we said that, the mean, in fact, was the least squares solution for minimizing that equation right there. Okay, just to remind ourselves, hopefully none of this is news to you, but also we could define the empirical standard deviation, which is almost, but not quite, here we're dividing by n minus 1 instead of n, almost but not quite the average squared deviation of the observed data minus the mean. And there's this shortcut formula right there for the this quantity. So that's the empirical variance. N minus 1 dividing into that is the empirical variance. The empirical standard deviation is, of course, just the square root of the empirical variance, defined right there. And we divide by n minus 1 right here. We divide by the n minus 1 just to get a so-called unbiased estimate. What that means, let me just describe briefly what that means, is if we were to, under certain statistical sampling properties, if we were to get new data over and over and over again, the average of these guys would in fact actually equal the population variance that it was trying to estimate. That's why we divide by the n-1 for this property called unbiasedness. So at any rate, the standard deviation is a measure of spread, whereas the mean was a measure of central tendency. And of course we divide by n-1 rather than n. That obviously doesn't change much. It's a factor of n-1 over n. If as n gets large, that doesn't make any difference, but it produces an unbiased estimate. Okay, so remember we had the process. If we took the data and subtracted off the mean, we got a zero mean process. If we take the data and we instead subtract off the mean, but then also divide by the empirical standard deviation, the resulting random variables, zi there, have both mean 0 and variance 1. So this is the process is called standard normalizing the data. And so it's centered at 0, and it no longer has units. Its units are expressed in standard deviations from the mean, right? So if something has a z value of 2, if zi equals 2, then that's going to imply that zi was 2 standard deviations from the empirical mean. It's often standardization is often very, very useful to get kind of unit-free quantities to compare across different across different measures. Okay, so there's normalization. Let's just briefly cover the empirical covariance. Okay, so the covariance between two random variables, and I write this in this class. I write covariance x comma y like that. What I mean is think of it. I think a lot of people taking this class probably have a computerish background. So think of this as, x is a vector and y is a vector, a list of numbers, and this covariance is a function. So this is a function that operates on these two vectors, and that's kind of what that notation means to me. It's not. I'm not defining it as the population covariance. This is an empirical quantity, but that's just a convenient way for me to write it, and you'll see how we use it frequently in the class. So the covariance is the sum of the products, the centered products, xi minus x bar, yi minus y bar. There's actually a shortcut formula right there. Again, just like the standard deviation, we divide by the n-1. So the correlation is related to the covariance in the sense that it's the covariance, which remember, notice the covariance, you're multiplying x's times y, so the units of the covariance are units of x times unit of y. If you want a unit-free measure, you would take this quantity, which has units of x times units of y, and then divide it by the product of the two standard deviations, standard deviation x and standard deviation of y. This has units of x, and that has units of y. And so the correlation is sort of a unit-free quantity. It varies between -1 and +1. A zero empirical correlation implies no linear relationship between the two variables. And this, of course, estimates a population quantity. If we have a sampling model, this estimates a population quantity, the population correlation. But for the time being, let's just think in terms of the sample correlation. Okay, so that's the sample covariance. We'll use that. Anyway, here's some facts I already covered, discussed a little bit about the correlation. The correlation doesn't matter whether it's correlation x comma y or correlation y comma x, you get the same number. It's between -1 and +1. It equals 1 or -1 only if the observations fall in a perfect line or positively or negatively sloped line. And then the correlation is a measure of the strength of the linear relationship. And then correlation equals 0 implies no relationship.